All right, class, let's dive deeper into series. In our last lesson, we saw how we were introduced to series through those triangular numbers. Let's see how we can apply triangular numbers into the next few examples, which are going to be a little bit more complicated. Okay, so let's take a look at 2 plus 5 plus 8 plus 11. If we do the same thing we did last time with triangular numbers, what we would say is that we have 2 dots and then we move on to 5 dots. It's not going 1 plus 2 plus 3 anymore. What we're going is 2 plus 5. And then we add 8. 3, 4, 5, 6, 7, 8. And then what do we have? 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, keep in mind that not only do we have these black dots, which actually form a triangle, we would also have the white dots that form next to it. So in addition to that, we would end up with 1, 2 white dots, 1, 2, 3, 4, 5 white dots. Notice how they all match up, right? They all match up. And then we have 8 white dots. 1, 2, 3, 4, 5. And then 6, 7, 8 white dots. And then you can just imagine we have 11 white dots up there, right? So I'll just put 11 there. All right, so how do we do this? Well, we can say, remember, we break this up into two triangles. Two triangles. The triangles are made up of 2 plus 5 plus 8 plus 11 is equal to one rectangle. What's one rectangle? It's made up of a height of 4 and a base of, how many black dots do we have? We have 11 black dots plus another 2 white dots. So we have 11 plus 2 in that case. Okay, so if we end up solving for this, we see that 2 plus 5 plus 8 plus 11, we can divide both sides by 2. So we end up with equals 4 times 11 plus 2, all divided by 2. And now we can see that 2 plus 5 plus 8 plus 11 is going to give us 4 divided by 2, or 2 times 13, and 2 times 13 is going to give us 26. Okay, so 2 plus 5 plus 8 plus 11 is 26. Well, you might just be asking yourself, well, why did I go through such a complicated process just to get to the value of 26? I could just as well have done 2 plus 5 plus 8 plus 11. That's a whole lot easier, right? Well, right now it's easier. But what happens if we end up with more terms? What if I were to ask you that same question with number 2 right here? 2 plus 5 plus 8 plus 11 plus all the way until, let's say I ask you to find the sum of 50 terms, right? T sub 50 is, we need to find 50 terms. So I don't even know. What is that 50th term, right? So we actually got to figure that out. What we do see here is that 2 plus 5 plus 8, this is showing us that we're always adding 3 every time. If you're always adding 3 every time, hopefully one thing that's coming into your head now is you're realizing, oh, this is actually going to be some kind of arithmetic sequence. It's arithmetic because you're adding the same term every time. And we know arithmetics always fall in line with some kind of y equals mx plus b. What's our m? That would be the slope. The slope is the common difference, the 3, times whatever term we're at, right? Plus that very starting value. What is our starting value? Well, keep in mind that the 2 right here that you see here, this is like case number 1. But we don't want case 1. We need to backtrack to find case 0. So if we're always adding 3, then that must mean that case 0 is subtracting 3. We'll get case 0 is actually going to be negative 1. Okay, so we want 3n minus 1. That's going to be our arithmetic sequence. Okay, so, the reason why we're creating this formula here is because I really don't know what is my 50th term. So I can now find it. If I want to find the 50th term, I'm going to say 3 is added 50 times, and then if I add that with the negative 1, the case 0, we'll get what t sub 50 is. Let's see, what is t sub 50? 3 times 50 is 150. 150 minus 1 is going to give us 149. So t sub 50 is 149. What is that showing us? Well, using our dots again, we've got 2 plus 5 plus 8. Now you don't really think I'm going to be adding or showing all these numbers, right? No way am I going to be doing that. But what I will do is realize, here's 2 plus 5 plus 8 plus yada, 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 all the way until, well, how many rows am I going to have? This is my first case, right? My first term, my second term, my third term. What term am I really going to go up to? Hopefully what you're saying at home is, oh, I know that I need this is going to represent my 50th term, right? So I'm going to have a total of 50 rows here then, okay? This is my 50th term here. And what is my 50th term? We said that value was 149. So what I need is 149 dots. And again, no way am I going to be drawing 149 dots, but what you do realize is yada, yada, yada. By the end, we'll end up with 149 black dots. Okay? Now, keep in mind the pattern that we're trying to see here is not only do you have the black dots, you also have the white dots. How many white dots will trail in after this? Remember, it's symmetric to whatever happened up here. So if you had 2 black dots, you should have 2 white dots here. Okay? And then how many white dots will you have? Then you'll have 5 white dots, right? And then you'll have 8 white dots, and so on and so on and so on. Okay, so what we're seeing here is that based on our formula, 2 triangles, the triangles are made up of the black dots and the white dots. Those dots are going to be 2 plus 5 plus 8 plus yada, 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 until we reach that 50th term, which is 149, right? So it looks like that. This is the formula for 2 triangles equaling 1 rectangle. What's 1 rectangle? Well, the height is this right here, right? This part right here, which is 50 rows. So we have 50 times, and then now our base is made up of 149 black dots, and don't forget this part, 2 additional white dots. So what we have is 50 times, sorry, this is hard to squeeze in here, is equal to 50 times 149 plus 2, like that. Okay? Now, what are we trying to solve for? We're looking for 2 plus 5 plus 8 all the way to 149. So we have to divide everything by 2. Okay? So 2 plus 5 plus 8 all the way to 149, which is our 50th term, is going to equal, let's see what this is. 50 divided by 2 is 25. And 25 times 151. 25 times 151 will give us 3,775 from my calculator here. Okay, so we get 3,775. All right, so that's how we can use triangular numbers, that pattern, to help us find now what we call a series, how we can add up a bunch of numbers together based on a pattern. Okay? All right, well, look at this. What happens now when we go to t sub n? What will that look like? Well, look at the formulas that you've created so far. 2 plus 5 plus 8 plus 11 was made up of 4 times 11 plus 2, all divided by 2. This one, 2 plus 5 plus 8 all the way to 149, or t sub 50, right? This is like your t sub 50, is equal to 50 times 149 plus 2, all divided by 2. Hopefully you're starting to see a pattern here, okay? What we're trying to see here is that this number here, it's basically kind of like that last term, right? This number here, the 11, is like your last term here. So if it's plus t sub n here, what we're going to say is, in the parentheses, this part, that 149 or the 11, is going to represent our t sub n in this case. Plus, what are we always adding to it? It always added 2, always added 2. We add 2 to it, okay? And then what was that number here, 50? What was this number here, 4? Well, isn't that just the number of terms we have? 1, 2, 3, 4. Right, 4 terms. 1, 2, 3, 4, all the way to 50 terms. So we're saying that this is the number of terms. Let's call it n. Okay. all divided by, what do they all have in common? They're all being divided by 2. Okay, so that's what this value is going to equal if we add it all the way to t sub n. Okay, well, what was t sub n? Well, remember how we created an arithmetic sequence for that? That was 3n minus 1. So we can turn this into n times 3n minus 1. Then we add 2 to it, all divided by 2, which equals n times 3n plus 1, simplifying, all over 2. There we go. N times 3n plus 1 all over 2. Okay? So in general, if we follow the same idea that we see right here, in general, the sum of an arithmetic sequence, right? This was a sequence because you're always adding 3 every time here, is what you do is you take the number of terms, that's the n value, let's say number of terms, and you multiply it by t sub n. What's t sub n in your sequence? Well, notice how it's always that last number. Sorry, it's very messy right now. But you can see here that it's always your last number. So number of terms times your last number. And then what do we do to that? We're adding that value of 2. What was that value of 2? Well, if you look at the dots, remember you're always adding, 2 plus 5 plus 8. Basically, it was the number that it started with, right? You have the 2, because that 2 got, it was symmetric over here. Those are the 2 white dots, which was symmetric to what you started off in your pattern here. Okay? So we're going to say it's the last term plus the first term. First term. Okay? All divided by, they all had something in common. They were all divided by 2 because you wanted to cut the rectangle in half. You didn't want 2 triangles, you only wanted 1 triangle. So you always divide it by 2. Okay, so this is our formula for the sum of an arithmetic sequence. Okay, let's try that. Now that we have a formula, let's find the sum of 3 plus 5 plus 7 plus 9. How do we get there? What do we do? Well, it looks like we're always adding 2, right? We see here, this is an arithmetic sequence, right? So because it's arithmetic, what is that nth term? Let's find out what it is. Well, our common difference is 2 times the number of terms. And if we go 1 back to find case 0, that'll take us to the value of 1, right? So we know that this is going to be the value of 1. So 2n plus 1 is going to be our arithmetic sequence formula. And so if we want to find the series now, adding everything up, we take the number of terms. I'm going to change the color. Number of terms. How many terms do we have? Well, there's n terms here, right? So we're going to say the number of terms. So we're going to call this S sub n equals n, number of terms, times last term. What's our last term? Well, whatever that is, right? Wherever the n is. So that's going to be 2n plus 1 plus the first term. Where's our first term? Take a look. It's right there, right? Our first term is at 3. All divided by 2. We want that rectangle to be cut in half, so we just have that one triangle giving us one series. Okay? And then from here, we just simplify just a little bit more. We're going to get n times 2n plus 1 plus 3 is going to give us 2n plus 4 all over 2. And if you want to simplify just a little bit more, you can factor out the 2. Even divide the 2 out once you do that, and then you'll end up with n times n plus 2, basically, like that, right? Okay? So, yeah, that's basically it. Okay? All right. Let's go on to the next problem. Find S sub n, the sum of the first n terms, and also find the first 4 partial sums, and then we're going to graph each of those. So number 4, 2 plus 4 plus 6 all the way to the nth term. Well, this is arithmetic, right? We see that it is adding 2 every time. So if we find that, that nth term, we know the common difference is 2 times n. And if we backtrack to case 0, that'll take us actually to 0, right? So therefore we have 2n plus 0, or basically just 2n, okay? So our t sub n is going to be 2n. All right, well, if that's the case, the first thing to do is find the actual sum. So to find the sum, remember we take the number of terms, which is, we don't know, let's call it n, times the last term, which is, what's our last term? Well, wherever n is. So that's going to be our 2n plus our first term. Our first term is 2 all over 2, like that. Okay, or that simplifies. We factor the 2 out. That simplifies to n times, and then divide by 2, right? So we'll have n times n plus 1, basically. Okay, or that gives us n squared plus n. Okay, now we know that this is actually going to look like a quadratic since it's an n squared. Okay, so that's going to help us in identifying what the graph will look like. All right, letter B, the first four partial sums. What it means is partial sums is, as you go from term to term, what are the actual sums? So for example, if we take n and then find the partial sum, s sub n, then if n is 1, then the sum is 2. When n is 2, then 2 plus 4, the sum will be of us 6. When you have 3, then we have 2 plus 4 plus 6, which will give us 12. And then finally, the fourth partial sum is if you add 2 plus 4 plus 6 plus 8, right? Or you can even plug into this formula here, right? We have the sum here. So 4 times 4 plus 1, right, is 5. So 4 times 5 is going to give us 20, like that. So we have 2, 6, 12, and 20. So then in part C, we're then asked to graph our partial sums. I don't have a whole lot of space here. Let's see, I'll do it here. So I'll have my graph. And keep in mind that the x value represents the n, the y value represents the s sub n. And since I'm going up to 20, I'll break it up 5, 10, 15, 20, like that. Okay? Like that. And then the n value will have 1, 2, 3, and 4, like that. All right, so then we plot that. 1 gives us 2. 2 gives us 6. 3 gives us 12. And 4 gives us 20, right there. Oh, that looks terrible. Oh, this is supposed to look like a quadratic, right? My quadratic probably didn't come out as nicely as I wanted it to. Basically what we see here is if you have n squared plus n, you know that you have a 0 at 0 and also at -1. So we know we have a 0 at 0 and -1. Just thinking about quadratics. So, your quadratic will look more something like this, Oops. Kind of off. But, you get the idea. It's kind of looking like that. Okay? Now, keep in mind, I think I mentioned this to you before, is technically we don't have a 1.5 term, right? We don't have a 1.75 term. So the graph I have here, in terms of graphing this quadratic, I do know that it shouldn't be a continuous line because I don't have all the points that exist in between. Oh my gosh, I'm just messing this up. Let's just draw it again. Okay, something like that. But what you should see is actually more a series of discrete points. And so I'm just going to draw my quadratic more like a dotted line, saying, it really doesn't have that entire parabola drawn in, but it's really supposed to be a series of discrete points. Okay, so just be aware of that because you don't have a 1.75 term, right, or a 2.1 term. All right, let's go on to number 5 here. 4 plus 10 plus 16 plus 22. Is this arithmetic? Let's see, what are we adding every time? Add 6, add 6. Yeah, we're adding 6 every time, right? So therefore, it's arithmetic. What's that arithmetic sequence? T sub n is, don't forget this is plus ... really. Okay, T sub n is, common difference, 6n. And what's the term that came before it? That'll be subtract 6, so we'll be at -2. Okay, so 6n minus 2. Therefore, we can now find our formula for the sum. So S sub n, this first n terms, is going to equal number of terms, we don't know, let's call it n, times last term, which is 6n minus 2, and then plus the first term. What's our first term? That would be 4, and all divided by 2. Okay, so S sub n is equal to n times 6n plus 2, all divided by 2. Or if we just simplify just a little bit more, we're going to get n, let's factor out the 2 actually, and we'll get 3n plus 1 all over 2. So we'll get n times 3n plus 1 basically. I'm just going to erase everything there. Okay, n times 3n plus 1. All right, well, now that we have that, we can find the sum of the first four terms, okay? So, oh, I'm running out of space here. This is going to be part B, the first four partial sums, n versus s sub n. We have 1, 2, 3, and 4. The first one's going to be 4, right? We add two terms, we'll get 14. We add three terms, 14 and 16, that'll give us 30. And then lastly, if we add 30 plus the other 22, we'll get 52. Okay, so those are our first four partial sums. And I'm just going to, let's just put it right there. I have a little bit of space there. N is our x-axis. S sub n is our y-axis. We're going all the way to 52. All right, so let's go to 60 then. So here's 30. So 10, 20, 30. I hope that is accurate. 40, 50. All right, there we go. Okay. 1, 2, 3, 4 terms. Okay, let's go ahead and plot that. So 1 is at 4, really far down. 2 is at 14, right around there. 3 is at 30. 3 is at 30. And 4 is at 52. 52. Right there. Okay, yeah, that kind of looks more quadratic than number 4, right? You can kind of see here, if I were to do this in a different color, that definitely looks a little bit more quadratic to me. So we've got our parabola going on there. Okay. All right. So let's go on to the next page, guys. So let's see here. Okay. Multiply it out. No shortcuts. All right. Well, let's go ahead and do that then. Let's multiply it out. This will actually help you on your homework as well. I believe there's a homework question involving multiplying these numbers out. No shortcuts, okay? All right, so let's do it. 1 times 1 is 1. 1 times, let's just do that. 1 plus x squared plus x cubed plus x to the fourth. I just multiply this 1 by everything in there. Now let's multiply the negative x times everything in there, okay? So we get, and then as I do this, I'm going to actually line up my common terms. So negative x times 1 will give us negative x. Negative x times x will give us negative x squared. Negative x times x cubed is negative x cubed. Negative x times x to the third is negative x to the fourth. And then lastly, negative x times x to the fourth is negative x to the fifth. And if I add everything up, align everything up, what we'll get is 1 cancels, 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 minus x to the fifth. That's what we'll get there. 1 minus x to the fifth. Okay. Next one. 1 times everything is 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth. And then let's do negative x times everything. So negative x times 1 is negative x. Again, I'll line up like terms. Negative x times x is negative x squared, negative x cubed, negative x to the fourth, negative x to the fifth, negative x to the sixth. And 1 cancels, 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 minus x to the sixth. Huh? Pretty cool, huh? All right, well, let's take a look at what's happening here. Use part A to find what 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth can be simplified to. Let's see here. What do we have? Well, what we know, I'm going to rewrite what we said. We said that 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth times 1 minus x is equal to 1 minus x to the sixth. Now, I'm going to use something that we actually learned back when we were working with triangular numbers. Remember with triangular numbers, we said that if we had two triangles equal to one rectangle, then if I just wanted to find one triangle, then what I can do is divide both sides by 2, because I just wanted the one triangle. That's the idea that we see here. If all I want is 1 plus x squared plus x cubed all the way to x to the fifth, then what we can do is divide both sides by 1 minus x. And that's it. I mean, there it is, right? 1 plus x squared all the way to x to the fifth is going to give us this value right there. That's it. Okay? So therefore, use part B to find the sum of, oh look, now we're actually plugging in the value of x. We see that x is the value of 2. So 1 plus 2 plus 2 squared plus 2 cubed plus 2 to the 4th plus 2 to the 5th. Let's use our formula. We're going to see that this is equal to 1 minus 2 to the 6th power over 1 minus 2, because the x was just the value of 2. Okay, if we plug that in, 2 to the 6 is what? 64. So 1 minus 64 would give us negative 63 over 1 minus 2 is negative 1. So we get the value of 63, like that. Okay? All right. Let's go on to the next part. In general, find the sum of 1 plus x squared plus x cubed all the way to x to the n. Well, try to find a pattern here. We did it all the way to x to the 5th. Now how can we do it to x to the n power? Let's see what we can create. There's the main idea. X to the 5th, you saw you got x to the 6th there. So this is going to give us 1 minus, that's in the formula we see there, 1 minus x to the, what does it become? You actually get the 1 degree higher, x to the n plus 1, all over 1 minus x. There we go. Okay? How will this change if it is a general geometric series? Well, keep in mind, in order for it to be a general geometric series, it doesn't always need to start with 1. This is the formula we created in which it always started with 1. Now let's see what happens when you actually have a t sub 1. It can change to whatever you want. Now with just a little bit of algebra, you can see that, as it turns out, each of these terms, it looks like they all have a t sub 1. So what I'm going to do is I'm actually going to factor out t sub 1 from everything. And what we're left with is 1 plus r squared, r cubed, all the way till r to the power of n minus 1, like that. Okay? All right, well, if this right here kind of vaguely resembles what we saw in this pattern here, notice how this is to the power of n minus 1, but this was to the power of n. But no matter what, you just take that power and you raise it 1 up, which means you raise this 1 up. So what we'll end up seeing is t sub 1, the number we factored out, times, and then in our formula we have 1 minus, and then notice how this was x to the n plus 1, right? We take that power, raise it 1. Well, we have the r value, the common ratio, to the power of, let's raise n minus 1 up. N minus 1 raised 1 is going to give us to the power of n, all over 1 minus our x value, or in this case, the r value. There we go. This right here is the formula for what we call the sum of a geometric series. Okay? So this is the sum of a geometric series. Compare that with the very beginning of our video, where we had the number of terms multiplied by the last term plus the first term, all divided by 2. This formula is the sum of an arithmetic series. Okay, so right now we've just created two formulas, the sum of a geometric and sum of an arithmetic series. Okay? All right, so I think we're going to stop there for today in our video, and then tomorrow, or not tomorrow, but in class during our Zoom session, that's when we'll actually start playing with these formulas and figuring out, do we have an arithmetic or geometric series? Okay, so stay tuned for that, and I'll see you guys in class. Adios.